We've talked about the importance of our time series being stationary. Unfortunately, at times, a time series is not stationary, and this will be obvious from the data that's observed for the time series. So the purpose of this section is to discuss how can we resolve this non-stationarity problem so that we can induce, let's say, an approximate stationarity with our time series. Along the way in this subsection, we're also going to introduce some notation that we will be using throughout the rest of this course. So to begin with here, one way to resolve non-stationarity when the problem is with respect to the mean of the series is by using something called differencing. And as I say here, we will be using this a lot. So what is differencing? Well, it's simply taking the differences between successive values in your time series. So for example, first differences are just simply take x of t minus x of t minus 1. What that means then is, let's say with your observed data throughout, you take x2 minus x1, x3 minus x2, x4 minus x3, and you do that throughout the rest of your time series that you've observed. And then this is what you use now as your, let's say, your new time series that you're going to then want to analyze, that you'll want to construct models for. Sometimes you'll see some books use this notation to represent the differencing aspect, where we have this triangle that's pointed down. You can kind of think of that as representing change. You change x of t. Second differences then correspond to, okay, you have these first differences. Now let's also do first differences of the first differences to get the second differences. So we take x of t minus x of t minus 1, subtract that from x of t minus 1 minus x of t minus 2. Okay, so why are we doing this? Again, this is to help resolve problems with the mean, non-stationarity due to the mean, meaning that the mean is changing over time. And first differences helps resolve, take out perhaps I shouldn't say perhaps, to take out linear trend that might be in the series. So for example, if I have my time series plotted like this, and if we see the points through time kind of going upward like this in like a linear manner, obviously in this particular case it seems like maybe the mean is the true mean is changing. So for lower values of t we have a lower true mean than higher values of t. What this is going to do, first differences, is going to take out that linear trend. Similarly, second differences help remove quadratic trend. Okay, so why does this work? Here's a simple proof to show this. So suppose you had the following, suppose your data comes about the following way. X of t is equal to some parameter beta 0 plus beta 1 times t. So it's like a regression model where we use t as the independent or explanatory variable. Then look what happens then with this, using this model. Look what happens when I take the first differences. I get beta 0 plus beta 1 times t minus beta 0 plus beta 1 times t minus 1. And if you go through the math, you're just left with beta 1 itself. So notice that this is no longer dependent upon t at all. And you will not have then this linear trend left over in these first differences. Okay, so let's take a look at an example. So I've actually simulated some data that I know has this linear trend in the time series. So let's look at how we do the first differences and look at the end result if we do the first differences. So the corresponding stuff that I do here is in the file nonstat.mean.r. And here is x1, here is x2, here is x3. So simply for first differences, if I look at t equal 1, look what happens. I have x1 minus x0. Well, I don't have an x0, so because of that, I can't calculate it. Then at time 2, I have x2 minus x1. In other words, 13.67 minus 1.31, and I get 12.36. Okay. So let me come on over here to our program. I'm going to read in the data. I'm going to look at the first 6 observations, the last 6 observations, compare that to the actual data file, which is a comma delimited file, just to make sure that I've read it in correctly, and indeed I have. Then we're going to do a plot of the data, like using usual methods. And what we see here is that it looks like there is a kind of a linear trend that's actually that's increasing through time. And let's take a look at the ACF plot too. This is a common characteristic that one will see when you have non-stationarity in the mean. The autocorrelations will be all high for a very long period of time relative to that x-axis. Let me come back over here to Word. Okay, so there's the same plot. And this is something, again, that's very common. Whenever you see a plot like this, and we will see many plots like this, immediately you should think of, okay, I got non-stationarity in the mean. Let's take a look at the first differences, see if that helps resolve the problem. Now, why are we having all of these high correlations here? High positive correlations, that is. Well, let's look back to the plot of the data. Notice how I end up having a lot of points that agree, relatively speaking, in their value, and they all are low. A lot of points up here that all agree with respect to their value, and they're all high. So, if we think of, let's say, in a simple case, you could have xt and xt minus 1 as 2 separate variables. Going back to your days of looking at regression, where you have 2 variables, and you want to examine just a regular old Pearson correlation between them. What we're seeing here, we have agreement in terms of the values. So because of that, then we're going to have high positive correlation. Another way to think about that is, let's say that we actually did do that with our data. I should say it's another way. Here's just another perspective of that. So what I want to do is form a new data set that has x of t and xt minus 1. So I'm just going to look at one time period back. This is going to be my 2 columns of my data. You can think of as maybe as 2 variables in a data set. Using methods that I've done before, I'm going to use the ts function to form x.ts. So I'm just transforming my data to something that R does recognize as a time series object, or have a class of ts. And then I use my ts.intersect function to help line everything up with respect to time. And so this is what we get. So for example, here's x2, and here's x1, here's x3, here's x2. So we can see that the second column here is xt minus 1. The first column is x of t. If I look at the regular old Pearson correlation between these 2 columns, I get 0.86. I use the core function to do that. And then I can do a plot of my data. So notice how I have xt on the y-axis, xt minus 1 on the x-axis, and we see this trend in the corresponding plot. And this corresponds to what you learned in your first stat course. Oh, you're going to have a large positive Pearson correlation. So that's why we see this for lag 1 of our ACF plot. You could do exactly the same thing for lag 2, lag 3, and so on. Okay, so the data is said to have non-stationarity in the mean because the mean of x of t, mu of t, appears to be changing as a function of time. Of course, we don't know what mu of t is, but we can see from our plot where our observed values are. It looks like something is going on where lower values have lower mu of t, and higher values of time have higher values of mu of t. And we did answer that second question. Okay, now let's take a look at how we can deal with the first differences. So I'm going to use the function diff for differences. And the first argument, I'm going to put in where my data is. And I'm going to put this here as lag 1. In other words, xt minus 1. So that's where the lag 1 comes from. And the differences, I'm just doing first differences. We'll look at other examples of argument values for the diff function shortly too, if this isn't completely clear, the argument values. I'm going to put that into an object called first.diff. And then if I look at the first 5 values in first.diff, here, for example, what we've already seen before is x2 minus x1. Let me just go back and verify that. Yep, there's x2 minus x1. Okay. Now, let's go ahead and do a plot of these first differences as well. So here is a plot over time for first.diff, and this is what we get. Notice I no longer have that linear trend at all. It's essentially disappeared. And we get a plot similar to what we've seen before, like for the AR1 case, where we did have stationarity in the mean. Now you might be thinking from this plot, well, wait a second, look it up here. You don't have as much variability as you do here. Maybe you have non-stationarity with respect to the variance. You got to be careful with looking too much into these plots. And I know from how I've actually simulated the data, I know I do not have non-stationarity with respect to the variance here. And so I think this is just due to sampling variability that we just so happen in this particular part of the plot, we don't have points that are going up as high. I mean, look at down here, we are having some points that do go down low, similar to what we have here. Okay, let's take a look at an ACF plot then of the first differences, and look how much different this looks with respect to the first differences. We no longer have those large positive autocorrelations like what we did before. And in fact, we only have one that's outside our, say, our borderlines to determine significance. Is the true autocorrelation equal to 0 or not equal to 0? Remember again, this line at lag 0 is not something for us to look at. So if I move along here in the notes, what about other types of differencing? How would we use the diff function in that particular setting? So for example, if I want second differences, then I can use the diff function again. I'm still using lag 1, but now I'm saying difference is equal to 2. So I'm working with xt minus 1, and since I have second differences, I'm doing differences on these differences. What if, though, you wanted something like this, x of t minus 2? You could do that as well. Now I use lag equal 2 here because I'm going 2 time periods into the past. Now this is something we haven't talked about yet because we focus on only going on 1 time period in the past. But doing something like this is of interest in particular settings when you have a seasonality component in your time series. So for example, like with the OSU enrollment data, notice how we have fall, spring, summer. Fall, spring, summer, observe every year. So essentially we have a seasonality aspect to our data. And perhaps we might want to look at x of t minus 3 in that particular setting, so that we will get to that as we go along in the semester. Maybe a simpler case to think about is that, let's say you're looking at something that's measured over quarters or maybe over months, and you expect to see the same patterns every quarter or every month across the years. In that particular case, you might want to look at, let's say, first differences with respect to a lag of 4 for quarter, or first differences with respect to a lag of 12 with respect to months. Now, we will have a whole section later in this course that talks about seasonality, so until then, don't worry about doing this kind of differencing. Now, how do you know if you need to do first differences or second differences and so on? Well, it will be fairly obvious from taking a look at the plot over time. Again, you look for, does that plot seem to have a trend in it? You can look at the ACF plot as well. There are, though, formal hypothesis tests that help you make that determination. They're called unit root testing, or it's called unit root testing. That will be more clear why it's called that name later on in the course. But I just wanted to bring it to your attention that there is formal hypothesis testing to help to make that decision. Some semesters I talk about the formal test, sometimes I don't. Very often, again, just from looking at those plots that I mentioned, you can make a good determination. Okay. Now, let's talk about something called a backshift operator. In all of statistics, at least in my experience, I think this is one of the weirdest notational devices that is used in statistics. It takes a little bit to get used to, but I think as you will see as we go along in the semester, it can be quite useful. And it's standard practice in a time series textbook and a time series course to use backshift operators, and we will use these a lot. So simply what a backshift operator is what most people refer to as B for backshift. And if I take B is not a number, B times x of t, all that means is that we have x of t minus 1. So B applied to something that has a time index causes the time index to backshift one time period. So we could also have b squared times x of t. That means now backshift 2 time periods. B cubed times x of t, that means backshift 3 time periods, and so on. Okay, so let's take a look at some notes here. So b itself is not any kind of number. Again, it just helps you work with that time index. And at times we might have, let's say, b times c, where c is some actual number, some constant. B times c is just going to be simply c, because there's no time index on c. Look at this. If I were to take 1 minus b, that quantity times x of t, look what happens. I get x of t times 1, and then I get negative b times x of t, which is a negative x of t minus 1. So it's my first differences. If I had b times b, I would get b squared. Then if I had 1 minus b, quantity squared times x of t, I can multiply all that stuff out inside the parentheses, do a little bit of math, and look what I get. I get second differences. Well, what if I had, let's say, 1 minus b raised to the 0 power? Well, just like any other case where you have, let's say, 2 to the 0 power, you get 1. The same thing happens here. And sometimes you'll hear people refer to as 1 minus b, that quantity times x of t, as a linear filter, because the linear trend is being, let's say, filtered out of the time series, because you get the first differences there. Okay, so let's look at how we can write some of our previous models that we've seen before in terms of this backshift operator. So previously with our moving average, we had this moving average of these we had this average value of these 3 w's. We can represent this instead like this: 1 plus b squared, that quantity times wt divided by 3. Because look what happens then. 1 times wt plus b times wt plus b squared times wt as well. I get WT plus WT minus 1 plus WT minus 2. What about for our autoregressive model? Well, what we can do here is, how about we move the x to t minus 1 part over to the left-hand side of the equation so that we have this. Now we can see that if I were to take 1 minus 0.7 times b, that quantity times x at t, I get my autoregressive part of that model. Okay, so let's take a look at another example where first differencing is needed for an actual observed time series. So later in this course, we will identify this model that I've displayed here as what's called an ARIMA 110 model. Excuse me. The 1 there corresponds to AR1. The second one corresponds to first differencing. And the 0 corresponds to a moving average component of the model. That we, in this case, we actually don't have one. Okay. So the model that we're going to look at then for our data looks like this. So we have that AR component like what we did before. Here's first differencing. And all that is then set equal to WT. How about we start multiplying stuff out and see how everything looks after that. So the first thing I'm going to do, I'm going to take 1 minus b times x of t. And so here's my first differences. Now you can more easily see. Then I take the 1 minus 0.7 times b times those first differences. So when I take the 1 times the x of t, I get, the 1 times the x of t minus x of t minus 1. So I get x of t minus x of t minus 1. Then I take the negative 0.7b times these first differences. And this is what I get here. And sorry, this is starting to get a little bit messy. And then I do a little bit more algebra here, and you can work through the details on your own, where now I have just x of t on my left-hand side. And now on my right-hand side, I have 1.7 times x sub t minus 1 minus 0.7 times x of t minus 2. So I go back 2 time periods, and then I have that white noise term at WT. Now, here's an actual realization or set of observed values from this particular time series. And what we can see in this plot is that we have non-stationarity with respect to the mean. Because again, we see some kind of trend that goes up, and then we see, and then eventually we see it go down. And so we can see, again, this data is representing what our time series is. It's not giving you what the true value is for the mean, but you would expect, just from what we see in our observed value, that the mu, let's say t here, is going to be less than the corresponding mu of t up there. Here's a plot and then the corresponding ACF, and once again we see the pattern that we had done previously in the previous non-stationarity in the mean data example, where we have these high autocorrelations. Remember, this is lag 0, and that is not important to us. Well, what would happen then if I take my first differences? So you can see I have my first differences on the y-axis. I have time on my x-axis. Now things are looking a lot better in terms of we no longer have that non-stationarity in the mean problem that we had previously. We also see somewhat trends. I gotta be careful what I mean by trends, but trends in terms of the dependence in our corresponding data. Because basically what we're doing here, we're plotting this part of the model. And so what we have here now plotted, I'm sorry, let me back up a second. So once we take into account the first differences then, well, what's the correct model then for what's left over? Well, it's an AR1. And we see then a plot here that looks very similar to an AR1 model that we've seen previously from other examples. We see those kinds of trends, that dependence over time, similar to what we've done or seen before. Here's now a plot of the ACF over the different lags. And so again, we don't look at this first autocorrelation, and we see we have two significant autocorrelations and maybe the third one at lag 3 as well. This again is completely fine. It's only when we have the large autocorrelations that go over a long period of time, if I were to draw them out like this, that's the only time that we would be concerned about non-stationarity in the mean remaining. Okay, so how did I actually come up with this particular data that I originally plotted? Well, I used a for loop in much the same way as I've done before. Let's just really briefly go through the process. So I'm going to set a seed so I can reproduce my results. I'm going to simulate 200 values of white noise from a normal distribution, that version of a white noise. And then where I'm going to save my x values that I get from my for loop, I'm going to put into a vector of length 200. To get my time series started, let me come back up here. Let me get the model so we can see that simultaneously. So to get my time series started, note that I'm not going to be able to calculate x1. I'm not going to be able to calculate x3. x2. I'm going to start at x3. So I have 1 point. Oops. Let me restate that. Excuse me. Look what happens when I have x1 here. I have 1.7 times x0 minus 0.7 times x negative 1 plus w1. I don't know what 0 is. I don't have a negative 1 as well. I need something though to start this process off so I can get an x1. And so that's the purpose of these two guys here. So that the x dot 1 is going to be there. X dot 2 is going to be there. 2 time periods in the past. Then for my for loop, I go for I in 1 to 200, the length of x. And I just simply plug in what my model is. Let me erase that. I plug in what my model is in the correct R syntax. And then once I find x sub I, then I reinitialize what x dot 1 is and what x dot 2 is as well. And then I continue in this for loop so that I can remove the dependence upon where I started my time series at an arbitrary point. I'm going to chop off just the first 100 of simulated values and just work with the last 100. And then this is how I did my corresponding plots. Okay. So we've talked about first differences, second differences, and so on. One could actually have fractional differencing. Okay, so you could see something like this. 1 minus b raised to the 0.5 power, for example. This can be useful in a situation where you have what's called a long memory time series, meaning that your autocorrelations, while we saw on previous ACF plots of the non-stationarity and the mean, we saw how those correlations do eventually go down. A long memory time series is that those autocorrelations are going to go down much slower. So there's a long memory. Long set of dependence. And in those particular cases, often a fractional differencing can be very helpful. We will have a whole subsection, or a whole subsection of our course where we talk about fractional differencing. You're not responsible for it right now. I just wanted to bring it up because often I have questions about that. Why do I have to use why do I have to use integers with the differencing? You can actually use non-integer values. Okay. Now we're going to talk about transformations of our time series, transformations of x of t. This discussion here is going to parallel some stuff that you would see typically in a regression setting, where you have non-constant variance and you need to figure out, well, how can I take care of that? Because a regular old regression model assumes you have constant variance. So what we can do is apply those same kinds of transformations that you would learn about in a regression course to x of t to help make the time series stationary in terms of the variance. So to examine this further, I'm going to take a look at an example from Shumway and Stouffer's time series analysis textbook. They look at earnings per share for the company Johnson & Johnson. This is kind of an old data set, but as you will see as you go along learning about time series, often oldies are goodies in terms of once textbook authors have found a really nice data set, they will continue using it for a long time. So anyway, so this data corresponds to something that's in Shumway and Stouffer's book. Their book has a particular package associated with it called ASTSA, which stands for, I believe, Applied Statistical Time Series Analysis. And the data is in an object in the package called JJ. So I'm going to take JJ, put it into an object called X. And this is what it looks like. So we have these earnings per share quarterly. This is, even though this data is old, this is still the way that companies report this kind of stuff over quarters. And we can do a plot then of the corresponding data, and this is what we get. And what we see over time, we see an upward trend, yes, similar to what we see before, so we have non-stationarity in the mean. But we also see how these data points tend to vary more throughout time. And so the variance is changing as well, and we need to figure out how can we handle that. Well, very often when you do a regression analysis and you see this kind of variability change as a function of your independent variable, the very first transformation that you try of your data is the natural log transformation. I'll just call it a log transformation. And so let's look at what happens if I were to apply a log transformation to the data. And this is what we get. This looks a lot better with respect to that variability than what we had in our previous plot. So generally speaking, I'm satisfied with what I see here. If I wasn't satisfied, I could use other common transformations such as maybe a square root transformation, an inverse transformation, and so on. Note that when you do that and you happen to have maybe in a different data set, maybe you have some negative values, well, you might have to make some adjustments so that you could actually take a log of that data. You could add a simple constant so that you would have all positive values. Now, sometimes in a regression course, you also learn about the Boxcox family of transformations that one could use to deal with the variance. You could apply those here as well. So if you haven't seen a Boxcox family of transformations before, it looks like this. Or let's say we create a new time series variable, we'll call it y of t. And for some constant that we're going to call lambda, if lambda does not equal 0, we can use this kind of weird looking transformation of our data. If though lambda is equal to 0, we could use simply the log transformation of our data. How do you come up with lambda? Well, there are ways that you can actually estimate it based upon your data. Now, in Shumway and Stouffer's book, they mention this possible transformation, but then they don't go ahead and implement it at all. If one wanted to implement it, there's not a way to do this in in the basic, let's say, stats package of R. But there are a few other time series, or I should say, few other packages out there that are meant for general time series analysis. And one of them that's popular is called the forecast package. And that provides some ways that you could actually estimate what this lambda would be and then apply it to your data. I have some corresponding code in my program if you want to see how to actually do that process. In the end, I think I end up with a lambda of 0.15. When I applied it to the data, then I used this little transformation, and I didn't really see any benefit from using that transformation versus using a log transformation. You're welcome to explore this further, but I tend to not do that in a time series analysis course. Now, if a variance stabilizing transformation is needed, generally speaking, it's recommended to do this before differencing. So, for example, if you feel as though you need a log transformation, well, do that first, and then do first differences amongst the log transformation. One little side benefit with these variance stabilizing transformations that you also will see in a regular regression context is that often this this helps with problems that might be associated with normality, as you will see in our class, where you will very often assume that we have a normal distribution for our x at t's, and like using a basic log transformation often makes things a lot better, and you can work with that assumption. Okay, so that's a really basic explanation then of how to deal with non-stationarity problems with your time series.